Today we're going to teach you a little bit about physical optics, specifically Rayleigh's criterion. To begin, we'll start with some background information. Physical optics is the section of optics that deals with the wave nature of light, specifically diffraction, interference, and polarization, among other things. Light experiences wave-particle duality, and the properties such as reflection and refraction can best be described with light acting as a particle. This is the basis of geometric optics. As for physical optics, interference, diffraction, and polarization prove the wave-particle duality of light. Interference arises when the electromagnetic fields of individual waves combine. They must be coherent and have identical wavelengths. Diffraction can most easily be explained by this principle, which states that waves spread out after they pass through slits, also when they pass around obstacles or by sharp edges. Lastly, polarization occurs when each atom produces a wave of its own orientation. This wave is said to be polarized if the electric field vibrates in the same direction at all times from a particular point. Now I'm going to talk a little bit about the history behind Rayleigh's criterion. English physicist Lord Rayleigh defined the limit of resolution as the separation between two stars when the bright center of one image lies in the dark interval of the other. This separation is said to be 1.22 times wavelength over the telescope aperture, or for visual light, 13.9 over telescope aperture seconds of arc. Rayleigh also investigated how accurately this objective should be calculated to avoid degradation of the area disk, otherwise known as the bright part of the diffraction pattern. This limit is found to be a quarter of the wavelength of light.
When 2 point sources of light are too close together, it is impossible to distinguish them from one another. This means they are considered unresolved. As the light sources move away from each other, it becomes possible to tell them apart, and they are considered resolved. At the point at which it first becomes possible to distinguish the light sources, they are considered just resolved. This occurs when the center of the diffraction pattern of one is directly overlapped by the first minimum of the diffraction pattern of the other. Rayleigh's criterion is an equation that helps determine this point. The equation is theta equals 1.22 lambda over d, where theta is the angle of separation of the light sources. Lambda is wavelength of the light, and d is aperture diameter, or the diameter of the hole through which light passes. Also, theta is measured in radians.
The purpose of Rayleigh's criterion is to show you the limits of resolution of a telescope aperture and to determine the separation angle between two light sources that are distinguishable from each other. It is used in telescopes, microscopes, and even the human eye. As for the human eye, Rayleigh's criterion helps to measure visual acuity using Snellen's chart. The most acute vision on Snellen's chart is within a factor of 2 of the visual limits imposed by diffraction. Okay, that's it, the end.